Welcome to my lecture series on mathematical preliminaries. In this video, I'll like to discuss eigenvalues and eigenvectors. Eigenvalues and eigenvectors are fundamental concepts in linear algebra, and that's why they are often used in structure mechanics and dynamics. These are associated with square matrices. Square matrices are those matrices whose rows and columns are equal. In order to understand eigenvalues and eigenvectors deeply, it is important to refresh our memories about linear maps. We discussed previously that linear maps transform a vector. So a linear map acts on a vector and gives us another vector. So in this example, L is a linear map and it is acting on a vector 5, 3. This results in another vector which is minus 1, 4. In an eigenanalysis, we have the transformation vector, transformation matrix, or a linear map that acts on a vector. However, the resulting vector is either stretched or squished as shown in this figure. So we have a vector v which is shown in purple. The linear map or the transformation matrix acts on it and it has stretched it to L of v, which is 4 times the original vector v. Thus, eigenvalues are scalar values that represent the scaling factor by which an eigenvector is stretched or compressed when a linear transformation is applied. In our current example, the eigenvalue is 4. Please note that the eigenvector is actually the non-zero vector that remain in the same direction after a linear transformation. So if we draw any unit vector in the direction of v, that will give us the eigenvector. So the vectors associated with the eigenvalues are essential in understanding the behavior of matrix under certain transformation. The eigenvectors can be scaled by their corresponding eigenvalues, but their direction remains unchanged. Mostly in the case of structure mechanics, our transformation matrix is symmetric. So, as we discussed, if we multiply our transformation matrix with a vector n, this will be equivalent to multiplying the vector n with a scalar value lambda. Thus, we can say that the vector n would either be stretched or squished when the transformation matrix is applied on the vector n. We can also visualize it by considering bunch of vectors of same magnitude arranged in a form of sphere. So we can see that there is one origin and there are many vectors radiating out of that origin in such a way that the magnitude of all these vectors are the same and they make a sphere. We select 3 vectors as n1, n2 and n3. When we multiply the transformation map T with the vectors n1, n2 and n3, in the case of eigenvalue, these 3 vectors would either be stretched or squished, but their direction will stay the same as before the applying the transformation. In order to solve the eigenvalue problem, we can bring the eigenvalue times n vector to the left hand side and then get the determinant of both the sides. Solving the determinant, we get a characteristic equation whose highest power is cubic, or in other words, we get a cubic characteristic equation. In this equation, we have 3 invariants or 3 coefficients which are defined as 1t, 2t and 3t. The invariant 1t is equal to sum of the diagonal elements of the transformation matrix. The second variable 2t is equal to t12 square, t13 square, t23 square all added minus t11 t22 minus t11 t33 minus t22 t33. Please note that t12, t13, t23, t11, t22 and t33 are all the components of the transformation matrix. The third invariant is the determinant of the transformation matrix. After solving this characteristic equation, we will get three values of the scalar lambda. In other words, we will get three eigenvalues. These eigenvalues can be put again in the general eigenvalue problem, and from there we will get the eigenvectors. Please note that the eigenvalue problem shown by multiplying the transformation matrix with n equal to the scalar lambda times n has got three equations in our 3D Cartesian space. However, these three equations are not independent.